Okay, good morning, class. We'll be treating today alkanes. In the last class, we talked about the alkanes. Alkanes are saturated hydrocarbons with sp3 hybridized carbon, while alkanes are unsaturated hydrocarbons with sp2 hybridized carbons. So wherever you see double bond, the hybridization is sp2. Whether in carbonate compound, that's CO, or in alkane, that is C double C. Okay. Wherever you see anything double bond, you're dealing with sp2. So let's know that. And whenever you see a saturated bond, what we are dealing with is the bond there, not the carbon. It's the bond that talked about the carbon. So when you ask about the hybridization of the atom in a compound, so look for the bond that the atom is connected to. The atom can be hydrogen, can be oxygen, can be carbon. Okay, so hybridization must not be necessarily for carbon. So I don't know whether you have an opportunity of having some of the past questions to know, because you're supposed to familiarize yourself with the way questions are asked. And that is the essence of the class work we normally do on Google Classroom, for you to have something, understand how the questions are asked. Okay, and that should also be part of your assessments. So let's take everything we're doing here serious. Thank you very much. So in this class, we're going to know what alkenes are. We're talking about the geometric isomerism. Remember, in the last two classes, we talked about the geometric isomerism, which are the trans and cis. So we're going to look at them. We're going to also consider their stability. In that geometric isomerism, which of them are more stable and why? How do we determine the stable isomer? And how are alkanes prepared and their properties? So these are what we're looking at in today's class. So at the end of this class, we should be able to answer these 5 questions. Okay. Now, alkanes, like we talked about, are known as olefins. Olefins, if you go to last class, when we talk about crude oil and their fractionations, you see the layer that we have olefins. So these alkanes are also part of a product of distillation. That's fractional distillation. Okay, and we say they are carbon-carbon double bonds. And in that case, we can have terminal alkanes and internal alkanes, and there are also cycloalkanes. Remember, we have cycloalkanes. The last class we had to talk about cycloalkanes, that alkanes that are in the ring form. The difference between them and this is because of the presence of double bond in that cycloalkanes that made it cycloalkanes. And we have internal alkanes, is when the double bond is in the middle of the compound. While terminal is when the double bond is at the end of carbon. So when the terminal carbon is bearing the double bond, we call it terminal alkanes. Now, with idea of physics you have, the most stable one should not be terminal, because the double bond at the terminal makes the stability to be tilting towards my own right. So one part will be the stuff to be wibbling. So the one that have I think my own left, the side that have heavier weight is going to tilt down. The side that have lesser weight is going to tilt up. So my right will be up. But looking at the internal ones, the weight is much more balanced. So when we are talking about stability,
So don't worry,
please, Abams, just mute them. Abosode, you're embarrassing me. How can you be in a class and you did not mute yourself? And you want somebody to mute you? This is a senior class, please. Before you even enter, mute yourself before you click join.
Stop now. Continue.
Mr. Alban, you can mute the person.
Yeah, muting and she's still on in the mic. Please, let's try to cooperate. We are almost done with the lecture so that we won't have problem. Please.
Okay, like I said, the internal are more stable than terminal because the weights are much more balanced in internal than in terminal. So when we're looking at stability of geometric alkanes, you should look at the balance of the weights. That's what we talk about the most stable and the less stable. So I'm giving you hits before we get to the slide. Like I said, our double bond is made up of two bonds. Somebody said, I can't hear you. Can you hear me? If you cannot hear me, let me hear, please.
We are hearing you, ma.
Okay, anybody that is not hearing, please check your network. So double bond is made up of one pi bond and one sigma bond, right? That pi bond is the weak bond that normally breaks during reaction. Now, if you look at saturated hydrocarbon like alkane, it's made up of only one bond, which is the sigma bond. So that sigma bond cannot break. And that is why alkanes are not reactive because they have only one bond. Whatever that happens, the compound breaks into two and will no longer be alkane. It is going to split. While pi bond is a weak bond that breaks in the reaction, and that is why alkanes are more reactive than the alkanes, because the pi bond is a sign of unsaturation, right? Now, if you're talking about, I don't know whether I did the demonstration for you in the class, the first class. And when we have a carbon is made up of 6 atoms. If you want to align the electronic configuration, which I know that my colleague that is a chemist have done for you, you're going to have 1s2, 2s2, and 2p2. And I said in hybridization, when we talk about hybridization, that is only the same energy level that is going to hybridize. So these atoms on the same energy level are going to hybridize. Okay, the hybridization should be energy level 2, 2, meaning 1s is not going to take part. Now, in that 2s has 1 orbital, while 2p has 3 orbitals. Now, in that 3 orbitals of 2p, remember, p has only 2 electrons. So during hybridization, which is mixing of atomic orbitals, 1s is going to lend 1 electron to p orbital. So the p orbital will be complete, x orbital will be complete. So we have 1s and 3p. And that's what happened in xp3, because 1s and 3p's are hybridizing in alkane. If you've not listened to the first class, I think I talked about it in the first class. Then that's why alkane saturated are sp3, because all the bonds during excitation state is being used in hybridization. Then when you come to alkane, now remember the p orbital has px, py, and pz. That's the 3 orbitals. We call them degenerate orbitals. So during hybridization in double bond, the z orbital is not participating in bonding. And that is why for alkene, we need 2 carbon. That's why alkene homologous series starts with carbon number 2, because for a compound to form double bond, they need 2 carbon. Why alkane can start with carbon number 1 because of saturation nature. Then having said that, this double bond, we have 2 carbons. So the last carbon, which is PZ, is going to be available to form double bond. So one carbon is going to release that one of the PZ. Another carbon will release another PZ. Remember, it is 2 electrons that make a bond. So that is why we're going to have 2 pi bond, because this pi bond is going to be contributed by each of the atoms. And remember, in this orbital, we have only one electrons. And there will be no bonding with one electron. That's why they say it takes two to tango. So for any bond to form, it is made up of two electrons. And the two atoms that form the bonding are contributors of that electrons that form the bond. So that is why in sp2, we have an orbital that is empty. That orbital that is not bonding is one they use in forming pi bond. And that's why it's only 2p that is bonding. We call it sp2. Because the last p is not available for bonding, is used in forming pi bond. And that is why in reaction, is that pi bond that is weak that breaks for reaction to occur. Now, when we go to sp3, that py, remember we have px, py, and pz. That py and pz will not be available for bonding. Just like alkene, it takes two carbon to form that triple bond. So that triple bond is from py and pz orbital. So both of these carbons are going to contribute these two electrons they are not using, making them to form two weak bonds, which is pi bonds. And when we get to alkynes, we are going to understand that in terms of reaction, if alkene need 1 mole of hydrogen, alkyne is going to need 2 mole because they have two empty orbitals. Unlike alkane that have one empty orbital. Then in alkane, all the orbitals are saturated. That's why they are filled up. So they don't have any space. And that's why in terms of reactions, alkanes are not reactive because there is no space. So now, coming to alkane, because of that pi bond and sigma bond, signify they have one double bond. And the hybridization is sp2, like I explained. The bond angle is 120 degrees. And the shape is trigonal planar. You're supposed to know the shape. You're supposed to know the bond angle and hybridization of each of these hydrocarbons. Please make sure you understand that. Now, in terms of isomerism, remember, when we talk about alkane, we talk about the geometric isomerism that occurs in alkane. We talk about chain isomerism. We talk about position isomerism. We talk about functional isomerism. But in alkene, the isomerism that occurs in alkenes are geometrical isomerism. These geometrical isomerism are cis and trans. Difference between alkane and alkane in isomerism is that alkanes are saturated. And because they are saturated, they can easily rotate. While in alkane, the double bond made it difficult for rotation to be feasible. And because of restriction in rotation, they have these forms of isomerism called cis and trans. Like we said in the 2 classes away, that when you talk about cis, talk about when priority atoms are on the same side of the carbon. And when you're talking about trans, talk about these priority atoms are in opposite sides. Can be atoms or group of atoms. Okay. Now, if you look at the slide, you can look at the slide of ash, like we said, is hydrogen. The black arm represents carbon, while the green represents, in this case, we can call it alkyl substituents. So hydrogen does not determine isomerism. What determines isomerism is atoms that have higher molecular weight. So in that case, hydrogen just have one. So any atom that is higher than 1 is going to determine the isomerism of that particular compound. So in the first compound, you can see the green ball are on the same side of the carbon. That's why we call them cis, and they can be represented with Z. While when they are on the opposite side, we call them trans, which can be represented with E. So that's how to predict the isomerism in double bond. Okay, we are continuing. Now, this is cis and trans terminology. Now, when we are talking about cis and trans, how do we know a compound that have cis and trans? Now, if alkene have 2 different substituents, there will be existence of cis or trans isomer. If there are 2 different, so if I have a carbon 1, if the first carbon has green The second carbon have only ash and ash, meaning hydrogen, hydrogen. There will be no isomerism there. So geometric isomerism will not be feasible there. Okay. And if if all of them have hydrogen, hydrogen, there will be no geometric isomerism. That's why the terminology is telling us that for there to be geometric isomerism, there must be two different substituents. Okay. And because of that, because they are restricted in rotation, when there are two different substituents on each of the carbon connected by double bond, we can say that this compound exhibits stereoisomerism called geometric isomerism. All terminal alkanes will not have trans or cis isomer. Remember, terminal alkanes, because the double bond does not balance the weight. So it means that one part of that carbon has more substituent than the other. So they will not have geometric isomerism. Now, for when I have isomer when I have one symmetrically disubstituted, when something is symmetrically disubstituted, it means that the weights are the same. They are same. If I divide them, they're going to give me two equal things. So there might not be existence of cis or trans isomers. So for there to be cis or trans isomer, there must be different substituents. Remember, this R is telling us the alkyl. And look at the double bond is internal, not terminal. So we're going to see some examples. Now, look at this double bond. On each of these double bond, number one, the carbon is terminal. And we have different substituents. So because of this position of this substituent, they can be the same side or different side, like we see in the first slide. We say that this compound is going to have geometric isomerism. So I'll look at where my priority carbons are, or group of atoms are. Then I will give them the name of the isomerism that they have. Let's go to another. Now, in that case, how do we determine the stability of this geometric isomerism? I will not read the slide. The slide is meant for you to read. I will only explain. Now, if you look at the compounds, now the first compound is 1-butene, meaning that if you look at that 1-butene, the first carbon, the substituent on the first carbon seems to does not have any isomer, because the first carbon has two white, meaning that hydrogen is 2. Because hydrogen is 2, there is no geometric or isomerism. That's why you can see it's called the 1-butene. Because for there to be isomerism, that first carbon is supposed to have different substituents. So look at the second one. We have two different substituents, making isomerism to be feasible. So in terms of isomerism, trans is more stable than cis. Remember what I talked about, because of balance of the substituents. In cis, the substituents are on the same side, causing the weight to be tilted that side where substituents are. While in trans, the substituents are on opposite side, making the substituents to be balanced. So the more the balance, the more stable a compound is. So increasing stability, but one does not have any isomerism. And look at the weight is towards one side more than the other. So it's highly unstable compared with cis. Because in that cis, each of the carbon has weight. But the problem is that the weights are on the same side. Then in trans, the weights are balanced because they are on opposite side of each of the carbon. So that's all about the stability. So when you're talking about stability, look at the substituents and how they are arranged. Okay, we are going to nomenclature. Remember when we're talking about nomenclature, the naming of organic compound, we talk about alkanes. The same thing happens whenever you want to name alkanes. What you're going to bear in mind is that I have to follow the route that I'm going to give this double bond, okay, minimal number. And following, talking about continuous carbon chain, it must cover the carbon that bears double bond. So looking at the structure, we can see the highlighted portion The highlighted portion is having CC double bond covered. So anything that is out of this highlighted portion become my substituents. Then am I following my left or following my right? I have to consider the double bond now because double bond is a functional group. Remember, the functional group is that atom or group of atoms that determines the reactivity of that particular compound. It gives the compound a name, identity, okay? The properties and everything because of the functionality. Okay, that's all. From functional group, we talk about functionality. How do you function? It's your functional group that determines your functionality. So this functionality of this compound is unsaturation because of double bond. So the functional group is double bond. That's why I'm following my left to make sure my double bond is supposed to be carbon number 2. Because if I follow my left, my double bond is going to be carbon number 4, which is not a good one. Okay. Then after every other substituent, I'm going to name them from my left, giving them the position they are on the continuous carbon chain. So that is why the naming of the compound becomes 2, 3, 5, because my substituents are in number carbon 2, 3, and 5, and my double bond is carbon number 2. So we say 2, 3, 5. All these substituents are the same. That's why I'll call them 3. And the substituents are methyl, trimethyl. And the compound is longest carbon chain of 6, hex. And in my carbon number 2, I have double bond. So I put 2 hexene. And remember I said I can also call it 2, 3, 5 trimethyl hex 2-in. Any of the method of naming is well accepted. Either you put 2 before you call the alkane, or you put the part of the alkane, put the number, and put the position. I'm telling you that in this hex, my double bond is carbon number 2. That's why I call it hex 2-in. And remember the protocol, number and number is supposed to be separated by comma. That's why we have 2, 3, and 5, Number and letter is separated by hyphen. Every other thing and everything you're writing is one word. So anything you're going to use either comma or hyphen, there's nothing again you're separating. So whenever you're writing it in theory and you write try and put space and write methyl, you failed it. Trimethyl is one word. Everything about the naming is the same word. There's no space. So anything you're having is comma or hyphen because of number and letter. I hope that's clear. Okay. Now I can also have 2 functional groups in a compound. I can have double bond and hydroxy group. I call it alkenol. Okay, so in that case, like I said, the higher takes the priority. So in that case, the priority compound becomes the alcohol, because in functional group hierarchy, alcohol is higher than alkane. Alcohol is higher than unsaturation. Unsaturation is higher than saturation. So in that case, if I remember, I said if I have triple bond and double bond, triple bond takes priority over double bond. So the compound will be named as triple bond. And if I have my alcohol and have double bond, alcohol is the baba. So that's why when I'm naming from the carbon that bears the hydroxy group as carbon number 1. And my double bond becomes 2. That's why I call it 2-propene-1-ol. I can also call it prop 2-in-1-ol. So the 2 is the same. In case you're in an exam where they're using OBJ and they are giving you options, and you're seeing option of talking about the homologous or the family before talking about the functionality. So I'll talk about prop -2-in-1-ol or 2-propene-1-ol. Both are very correct. Okay, going to the next compound, you can see we have a long hydrocarbon, which is hept. Hept meaning the carbon number is 7. So in that case, my carbon number 2 is where my hydroxy group is, and carbon number 6 is where my unsaturation is. So, and that's carbon number 6. I also have a compound called methyl. So I will say 6-methyl. Remember, substituent come before functionality. 6-methyl, 6-heptene, 2-ol, or 6-methyl, hept, 6-ene, 2-ol. So that's the same method of naming. So whenever you want to name your alkene, look at the longest continuous carbon chain. Consider the functional group if there are more than one. Then give them hierarchy. If there's any other compound like carboxylic acid, like alcohol, other than double bond, give those the priority. And if it's only double bond, give the double bond priority. Then follow the route that will give this double bond the minimum number on continuous carbon chain. Then when you're done, circle anything that does not fall in the line of this continuous carbon chain, they become substituents. Then go and if there are more than one substituent, start naming them alphabetically, irrespective of their position in continuous carbon chain. Okay, if I have bromo and I have chloro, and my bromo is 5, while my chloro is 2, I will go 5 bromo before I go 2 chloro. Respective of their position, I must name them alphabetically, indicating their position in continuous carbon chain. So that's all about alkene and naming. So what are the properties of this alkene? The properties of alkene, like we talk about, because of this double bond, we have weak van der Waals interaction, and their physical properties are similar to that of alkane of comparable molecular weight. Whenever you're comparing hydrocarbons, you have to compare them with their molecular weight. I cannot compare propane with heptane, cannot work. You have to compare them with their molecular weight, comparable. So alkane have low melting point and boiling point. Okay, they are like you see in alkanes, their melting point and boiling point are going to be increased as carbon atom increases. Okay, because there will be increase in surface area. Now, in terms of solubility, they are soluble in organic solvent, just like alkane, because they are all hydrocarbons. So now the CC double bond, single bond, between the alkyl group and one of the double bond can slightly initiate polarity. Okay, because of double bond that donates electron density, meaning that in terms of polarity, alkenes are more polar than alkanes. But their difference is little. The difference is because of this double bond have electron donating potential. So now look at the slide. You can see this. I have to expand it for you to see it. Now, in terms of character, I think we talk about the character of this sp2 and sp3. sp2 character, sp3 character is 25s character. Remember, if you look at the orbitals we have is in sp3 is 4 orbitals, 1 for s and 3 for b. So when you divide by 100, you realize that s is going to have 25, while p is going to have 75. Okay, so that is why we say that sp3 has 25s character and 75p character. But if you look at sp2, you realize that the p character is what you're going to do. You're going to divide all by 3. When you divide 100 by 3, you're going to get 33.3, approximately 33. But because p is more, so we're going to have 33 for s and 66 for p. So that's how to know the x character and p character of. Then if you come to sp, if you divide 100 by 2, you're going to have 50. So we have 50 s character and 50 p character. Make sure you understand the character, the s character of all these hybridized carbons. What we need to do, divide them by 100, depending on how the percentage of s and p, then you know them. Okay, now my sp2, because of this C of double bond, Now, alkyl are electron donors. Alkyl are electron donors. So they're going to donate electron to this carbon that is connected to double bond, causing that electron density on that double bond to be increased. So that is why alkenes are more polar than alkanes, but their polarity is not pronounced. Okay? They're not pronounced polarity like the one of alcohol, because alcohol own is due to hydrogen bonding. Okay, but this one is because of electron donating potential of this alkyl. Now, whenever there is, in terms of boiling point, now look at, we have trans, we have cis. The more polar compound are the trans, right? Because if you look at the cis, we have balanced weight. So weight from A balances the weight from B. So make the net pole, there's no net pole. That's what made them to have lower boiling point. But look at the one of trans, of cis. There tension. I'm donating. So there's excess electron density. So making it to be more polar, and there is small net dipole. Hence, cis isomers have higher boiling point than trans isomers. When a compound is stable, there is no wahala. When you have money, your boiling point is low. Even if somebody fights you, you don't react. When you don't have money, and you have load, even when some people are, something is not supposed to cause wahala, because you are already tensed up, you react. That's why Cs are having higher boiling point, because tension is more than trans that is well stabilized. There's no shaking. Okay, so the more stable, the lower the boiling point. The more unstable, that's what we talk about. When a compound is unstable, compound tends to react faster, because within itself it is already reactive. But when a compound is very stable, you have to look for something that can make the compound react. That's whenever you talk about a catalyst being involved, it means that the compound is so relaxed. We need something to agitate it. Okay, in life, whenever you're living life of ease, you're very stable. At times, what makes us to do well is when there is any problem or challenge. You stand up and you want to show what you can do. When you wake up in the morning and there is money and there is food everywhere, you tend to be lazy. But when you know there is a responsibility, you tend to react to do something. So that's what difference between stability and instability, by virtue of low boiling point and high boiling point, and in terms of reactivity too. Okay. Now, these are some of the alkenes that you can talk about that is available over you. Polyethylene. If you look at those days, you say, I'm going to buy polyethylene bag. That is polyethylene. Polyethylene, it is when you have methylene. You can see this ethylene now. When there are more than one ethylene are going to be coming together to form a compound ethylene, we call it polyethylene, by process called polymerization reaction. So when these monomers, which is ethylene, combine together to form polymer, we call them polyethylene. And these are the compounds we use in all these PET bottles and packaging nylon and films. Ethanol is another compound that we can get from alkane. This ethanol is fuel addictive, is a solvent. Ethanol is what they use in preparing agbo. Remember, we have a natural one and we have the one we can obtain from alkane by process of hydration. We're going to see them when we're talking about reactions of alkene. So we also have ethylene glycol. Ethylene glycol is antifreeze. Is an antifreeze. We also have polystyrene. Polystyrene is what we use in plastics, in molded plastics. So some of these compounds you're seeing are what we can see around us. They are useful in our industry. We see polyvinyl acetate. We see polyvinyl chloride. the one you use in your films, while polyvalent acetate is used in your paints. The essence of this is that whatever you're studying in organic chemistry is not useless. It is what you can relate around you. Okay? So look at, in nature, we also have alkanes in nature. Your carrots, your ginger, your lemon, they all have, even your apple, they all have a compound that has double bond. This double bond makes this compound very healthy. That is what made them to be, that when a compound is unsaturated, the compound is very healthy for skin. It's an antioxidant. The more the double bond, the higher the antioxidant potential. Okay, that is why beta carotene is very good, because of, you can see that it's made up of so many unsaturation. Double bond is too much, so that's why it's very healthy. Okay, so whenever you come, that's why when you see, when oil, when we get to oil and fat to talk about it, let me not talk about it here. So now we are here already. So alkene, also you can see when you have stearic acid, look at stearic acid. The structure of stearic acid, you can see the more the double bond, the lower the boiling point. And that is what infers that whenever you have oil and fat has higher, I'm talking about melting point. Fat has higher melting point because it's solid. Why? Because if you look at stearic acid, there is no unsaturation. The only double bond we have is one that connects to hydroxy group. That's the carboxylic functional group. But when we have one double bond, we have melting point to reduce to 4. When we have 2, it has reduced to -5. When we have 3, it has reduced to -11. So the more the double bond, the more liquid a compound is. So that's the difference between your fat and oil. That's the difference between your fat and oil. Fats, okay, and oil are triglycerols. They have different physical properties. While fat have higher melting point because they are solid at room temperature. That's why you can get your margarine and put it outside the fridge. You can set it till eternity, even when the sun is hot. While oil cannot, you don't need oil. When oil is outside, oil is supposed to be liquid. So whenever I see oil that is sleeping when there is rain, that oil is not a good oil. Oil are supposed to have lower melting point, meaning they're supposed to be liquid at room temperature. Okay. Now, if you want to get a good oil, go and bring your oil, put it in the fridge at temperature of 4 degrees, not freezer. If that oil,
Who is this person? Who is that person now?
The truth that some people I'm going to remove from the class. And I mean it, in the next class, I will start removing people. In the next class, as soon as I come, people make noise. I will just remove them from the class. This is the last warning. I've been warning from the beginning of the class. And yet, if we cannot do these simple things, what is being educated? Being educated is not about reading, knowing how to read and write. Some of these things are what makes you educated. So they can be able to carry yourself out. You can't just be behaving like an illiterate and you are educated. These are senior students, for crying out loud. Please.
I'm sorry, ma. I'm sorry.
It's fine. Okay, like I said, oil have lower melting point because they're liquid at room temperature. So make sure you get a good oil. Whenever you buy your oil, if you put it in a normal fridge and you see your oil blocking, that is not oil. That's not a good one. Okay. Now, like we said, when you talk about saturation and unsaturation, that's what talks about fat as saturated oils, while unsaturated are oils. So unsaturated, when vegetable oil are unsaturated. Now, if you look at coconut oil, some coconut oil are saturated. The coconut oil has high level of saturation, but it's very healthy fats. There's a compound called lauric acid. Lauric acid is what makes coconut oil very healthy. Despite they can be saturated, but they're very healthy. So They say an exception to this generalization is coconut oil, which is largely composed of saturated alkyl side chain, yet healthy. So that's why coconut oil is one of the healthiest oil apart from olive oil. So you can use coconut oil for your meal. Okay, we're talking about the reactions. I don't want to rush us in this class, so I'm not going to finish this class today. I don't want to rush us. This is something I can easily finish today, or should I finish it today? So I want us to take it easy, especially in the reaction. But the reaction is what I want us to understand very well. So I'm going to introduce the reactions and finish the reactions in the next class. So we can go and digest what we've talked about so far. Okay, so let's talk about the preparation. Preparation, whenever you're talking about preparation, the most common preparation you're going to have is dehydration. Now, when we are going to talk about the reaction, you're going to see how hydration is going to form alcohol. Hydration of alkene is going to form alcohol. So dehydration of alcohol is going to form your alkene. So that's the method I want you to know about today, the dehydration of alcohol. In that dehydration, you need sulfuric acid. Sulfuric acid is a dehydrated agent. That's when you see somebody's skin, that they pour acid on somebody's skin, you can see that place is going to be dried and start peeling. That drying is mean that it has taken away water from that place and shrink that place. So that is dehydration. So that dehydration is removal of water. So, and in that case, in this reaction, that's the sense of being in class, there's a temperature required for this dehydration to occur. That temperature is 170 degrees Celsius. So you have to put it sulfuric acid, H2SO4, and it's supposed to be conc H2SO4 at temperature of 170 degrees for me to have dehydration of alcohol to form alkene. For your level, that is what you need to know here. Okay, we can also have tertiary butoxide. In that case, what it does is that it's going to remove my hydrogen bromide from this compound to form double bond. Why conc sulfuric acid is going to remove water. And removing water is going to remove hydroxy group from the carbon that bears the hydroxy group and hydrogen from either of the carbon, either left or right. So you cannot remove both hydrogen and hydroxy group from the same carbon, from adjacent carbon. So the major product or the minor product is determined from the carbon is going to remove the hydrogen from. If from one, you can realize that my hydrogen is going to come from I'm going to have hydrogen from the carbon number 3. Okay. And that carbon number 3, I can have this cis or trans. And major product is always the most stable product. That's why we have our most stable product to be major, because it's stable. Then the last compound is when my hydrogen is coming from carbon number 1. So that's why I'm going to have a compound that does not have isomerism. Okay. All right. So ask your question, because I want to start the reaction and I don't want to stop when I start. So in the next class, we're going to talk about the reactions of alkene. So after talking about the reactions of alkene in the next class, because I'm going to use 2 hours. So if we can do next week, Monday by 8, that will be fine by me. So we can do 8 to 10 if it's okay by you. If it's okay by you. But if it's not okay by you, we can also go to a normal time. But I feel that this time is very good. So you can go about whatever you want to do. So we're going to do reactions of alkene in the next class. And we're going to also talk about alkyne. Alkyne is very small. It's not as long as alkene. Then after which, the upper week, we are going to talk about benzene and aromatic compounds, which will be the last class. That's benzene. I just want to give it to you as Jara, so you can have idea of aromatic hydrocarbons. So let's ask our questions here. So I want to draw the curtain here, because I want us to treat reactions in the next class. So ask your questions. No question? which is assumed that the class is well understood. Please, Cosrep was not in class today.
I'm in class, so you change
He
your
came in
Zoom.
later.
You change your Zoom link. I went to the other one, so I was the only one on that. You change
Okay,
your
sorry.
link.
Yes, but I
Yes,
shared it now. I shared it.
Before I get to know, it's already
Okay.
past 8, so I had to join the new one.
Right.
Then secondly, man, you were talking about putting oil inside the fridge, but somebody distracted you, so you didn't finish the explanation on that.
Okay. So I said if you want to know a good oil, when you buy oil, put it inside fridge. And if that oil solidifies, that oil is not good. A good oil should be able to stay in the fridge at temperature of 4 degrees and not solidify. Yeah.
Okay. Thank you, man.
Yeah. Welcome. So all those
Please,
oil that you see that when it's
Yeah,
raining,
Hello,
there's
ma.
some oil that when it's raining, you start seeing that oil, they start blocking. That oil that is not good. Either the oil contains a high level of moisture or the oil is contaminated.
Hello,
okay,
ma.
ma.
also,
Okay, I can
please,
hear you.
Hello, ma.
One
please,
at
ma. So I want to ask that.
One at a
So
time, please.
I raise up my
Please,
hand, ma.
raise up
Okay,
your hand.
please let's hear David.
Yes, ma. Good morning, ma.
Good morning, David.
And thank you for the session. Ma, my question is on when you are explaining sp3 hybridization of that have carbon of 25% S character. You said you 100 have to be divided. Ma, can you hear me, ma?
Okay, continue. Okay, I
Yes,
can
that
hear you.
100 have to be divided by 3 or 2. I don't get that explanation well, ma'am.
Okay, all right. Let me explain. SP3. In SP3, how many orbitals do we have in SP3?
4
David, answer
orbitals.
me. 4 orbitals. So if I divide 4 orbitals by 2, if I divide 100 by 4, what will I get?
Okay, you get 25, ma'am.
Now, because it's SP3, my P has 3 and my S has 1. So I have to give them by virtue of their number. So my S is going to have 1, which is 25. While my P is going to have 3, which is 25 times 3. Do you understand? Then in SP2, meaning that I'm going to divide 100 by 3 because S is 1 and P is 3. So when I divide them, I'll share them accordingly. P is the whatever I got by 2, while S is whatever I got by 1. In SP, I'm going to divide 100 by 2, meaning they're equal. So S and P are going to have equal character in percent.
50%.
That's 50-50, yes. So S in triple bond, S has 50% S character. While in SP2, S has 33% S character. While in SP3, S has 25 S character.
Okay, ma'am. Thank you, ma'am.
Welcome. Any other question? So David, move your hand. David, type.
Please, ma, I have an
Good.
information. I have
Okay.
an information to pass across to you. One of us has been hospitalized for the past 1 week now. So
Oh,
his name is Adebanjo Wasiu. He has not been attending the classes we've been having since last week. So he forwarded the picture of his being hospitalized to me. So he asked me to take a permission from you
it's fine.
that he
It's
won't be
fine.
in the class.
Okay, tell him to whenever he come from class, he should go to the YouTube and watch the class and listen to the class and then do the assignment
Okay.
and so.
Very good.
All right.
Thank you.
Welcome. So Ayetibo. Hey, sorry.
Yes, ma. Ayetibo.
Maria, the floor is yours.
Yes, all right. Good morning, ma.
Okay,
Thank you so very
Ayetibo.
much for the
Sorry.
class. Okay. Please, ma, I want to ask, you said something about oils. And I want to ask that usually the palm oil we have with Olaine and all of that is usually viscous.
Sorry, a call
Doesn't
is coming
it?
to interrupt us. Okay. So start all over
I said
again.
palm oil is usually
Uh,
viscous.
Okay, yes, it's meant to be
Yes,
viscous.
usually viscous, yes, and thicker than regular vegetable oil. How does it make it very healthy?
Now, you know, some of those palm oil that is very thick is because some of them has water added to it.
Oh, okay.
Some of them, you know, some of them is because of water. Okay. Normally, palm oil is not supposed, it's supposed to be thick, but not very thick. There's some oil that before you remove them, you have to melt them. Those ones they're not very that because of water. And those oil, when you allow them to stay for a longer time, they become rancid faster because of presence of moisture inside them.
Yes, that's true.
So it's because of moisture. You know, even some oil now, you realize that some oil have been they've added so
Adulterated.
many rubbish. Yeah, adulterated, yes. So that just, but when you get a good oil, it's supposed to flow. And whenever your palm oil is sleeping, that oil has high level of moisture and is contaminated. Even palm oil is not supposed to sleep. It's supposed to flow even when the weather is hot, is cold. We see some oil when the weather is cold, because they are sleeping. They're not supposed to. So let's be careful of the oil we take, please.
Okay, thank you very much.
Thank you. If you've not connected to me via my YouTube channel of Ask Dr. Anita, please go and watch so that we can prevent some things. Some of the problem we are having in life is our intake. There's some things you can prevent by eating right. They said, let your food be your medicine and your medicine be your food. Please, if you're not there, go and watch your blood type diet. Understand your blood group and what you're supposed to take and what you're not meant to take.
Okay, thank you, Ma.
All right, thank you. So I think I will see you guys in the next class. So let me know if we are doing the same time, which I would prefer it. If it's workable for us, let's maintain it for the next 2 classes when we are going to be rounding up. And please, if that you have any question, you can ask that question on the general platform so others can learn from it. I can make a voice note to explain if you have any question. Okay.
Thank you,
So
ma'am.
Good morning, ma.
good morning.
Good morning. How are you doing, ma?
I'm very well, and you?
Please, ma, I don't know if you can help us with some of your past papers so that we can review in our leisure time.
As in past questions.
Yes,
ma'am.
over the years, so that we can review and see the nature of your paper, and then probably we'll be able to ask questions in the coming sessions.
Okay, I'll do. I'm on leave now, so it's whenever I get to school. So maybe when I resume from my leave before the last class, I'm going to send it out. But by next week, I'll still be on leave, so I might not give you. But after next week, after next class, your last class, I'm going to give you past questions.
Okay.
Thank you.
Please, ma. When we got to the Google class, we found out that some names were appended there, and some of us names were not among those names. So
No.
I don't know.
The people that names that are there. You joined the Google classroom yourself, except you did not join. Did you join? Do you have the first link to join?
Yeah, I've joined, even submitted my assignment there.
Yeah, so you're there. When you get there, you might not see your name because you're there. You will not see your name. You see other people's name.
Okay.
Yes.
Okay.
Do you understand?
Okay.
Yeah.
Hello, ma.
Yes.
Hello, I can see you. Oluwakemi.
Yes, ma. In the Google Classroom, I did not find my name there. But and then I also
were you able to submit?
I don't know whether it was submitted or not. I had a lot of difficulty yesterday submitting it.
Don't worry. I will take all your names. The only thing the cost will give me is give me the comprehensive list of names.
Then, man, another issue I had was this. Can I talk now? I
Please,
realize
Who is
that.
other people? Please, if you are not talking, move.
let's hear Oluwakemi, please.
Okay,
Only
ma.
one person.
Yes, I had a.
Oluwakemi. Oluwakemi is not talking again.
Okay, hello, ma. Okay,
Okay.
I'm on now. Yes, I realized that after submission, I saw that, and then I opened again. I saw that one of my numbers was missing. So, and I tried to, I unsubmitted, then tried to submit again, but it was not going. Although I still eventually was able to do it, but I didn't know whether it's actually submitted. With the full page. I was frustrated yesterday, but I could not give up. I had to just submitted something.
Please don't give up. I will look at it. Don't give up.
Okay. Hello, ma. Can I request for something?
Okay.
I don't know if you can extend the day of submission. Let me try and see if I can submit another one. I can't. I don't know if I'm speaking for other people. Maybe extend it today.
You worry a lot. You can worry for Africa. You can worry for Africa. I will check for your name.
All right, ma. All right. Okay, ma.
Hello, ma. Good morning.
Thank you so much.
Hello, ma. Good morning.
Good morning, Koroma.
Yes, I have the same problem with Oluwake, ma. I've been trying to submit, but it's showing as if it didn't go. So we don't know if there is a way for you to allow us to resubmit again.
No, what will happen is that let the course rep give me comprehensive list of students. So I'll go and check. If there are people that did not submit, then I can extend the submitting window.
All right, ma. Thank you very much, ma.
All right.
Thank you,
Yes,
ma.
One after the other, please. After the other.
Good morning, ma.
Good morning. You guys are waiting for me today with questions. Now they bombard me like this. At the end.
Let us do it in order. Okay, it's
Oh yeah. Let's hear you one after the other.
One after the other, please. Put your hand up so that another person will not interfere when you are speaking.
Okay, let's hear Lawal. Lawal, unmute yourself.
All right, thank you, ma. Good morning, ma.
Good morning.
Yes, ma. Please, ma. I'm sorry I was not available when you called the attendance, ma. The network logged me out, so I don't know
No.
if you can help look into that.
So it means that you were not in class, I mean. You're telling me that you were not in class.
No, it's on the network, ma.
Okay, there's no worry now. So just go and make sure you listen to the class, and I'm going to give assignment after the next class. So make sure you attend to the assignment.
All right, ma. Thank you, ma.
Any other question?
Hello, ma. Good morning, ma.
Good morning, ma.
Hello, ma. Good morning, ma.
Good morning, I can hear you.
Okay, ma. It's actually concerning the timing, ma. 8 o'clock is kind of, because between 7 and 8, we'll be rushing to work. So I think 9.
Okay, fine.
I think
So
9 will be fine,
8 o'clock. Okay, no, we can revert back to our normal time. We can revert back to our normal time, right? Hello?
9 is fine, ma. 9 is fine, ma.
Okay, 9. Okay, 9. Okay. Okay, fine. So we can do 9 on next week Monday is fine. 9 is fine. So we can do 9 to 11. Any other question?
Good morning, ma.
Good morning. I can hear you. Go ahead. Who is talking?
Maybe network issue.
Good morning, ma.
I can hear you.
Good morning, ma. Yeah, please, ma, you called my name earlier. I just said my name, then after seconds, I couldn't hear it again. Yes, ma. Maybe it was, I think it was network issue.
I was said you are the one that was disturbing my class when you came in.
Yes,
That's
ma.
why I called you. I called you because you are disturbing me.
Sorry, ma.
That's why I called you. Unmuted yourself and you were
I'm so
crying with
sorry,
your
ma.
baby was crying. Noise was everywhere.
Sorry, ma. I'm very sorry, ma. I don't know. I'm very sorry. Yes, ma. Yes, ma.
No worries. All right, everyone. So see you guys in next class. Next week is going to be by, like we said, you're going to be having it by 9 next week, right? So see you then.
Thank
So
you,
if there's
ma.
any need for assignment, I will send it. I will send an alert to you before next week, and I'll give you a deadline for submission like usual.
All right,
Okay.
ma. Thank you, ma.
Bye.
Remain blessed, ma. Yes, ma.
You
Take
too.
care of yourself, ma.
Don't forget to promise
Thank you.
get back to us for signing the test, ma. The assignment, ma.
Can be stop for
Yes.
Africa.
Yeah, they can. Shabi Oluwa Kemi. Is
Yes,
Oluwa
ma.
Kemi
Yes,
like?
ma.
I know you
Yes.
now. You can work for Africa. I hope you're not the
I'm
last
sorry
born.
about that.
Hi.
I'm sorry about that. No, but I don't want to be frustrated.
Let the course get back to me on the attendance so I can use it to view the submission list.
Okay, ma. Thank